Welcome everyone, and as Malu mentioned, this is the second session we are having with Eden, so I'll keep this introduction very short. So Eden comes with a background in physics and electrical engineering. He previously worked as a signal processing algorithm developer at Apple, and then he moved on to complete his further education in quantum, advanced education in quantum dynamics at Imperial College London. He also co-founded the Imperial Quantum Tech Society, and now at Classiq, he is working as managing all of exciting stuff over there. With Womanium, he has joined to deliver the course, but also take care of a project in Womanium Classiq collaborations. We'll learn about that too. So with that, let's welcome Eden. Over to you, Eden.
Thank you very much, Vardaan, for again introducing me so nicely. Can you hear me well and see my screen?
Yes.
Perfect. So last time we discussed about the Classiq 101. It was the first introductory session to Classiq and what's going on with quantum algorithm development in general. In today's session, we're doing the first part of two sessions of quantum primitives with Classiq. And there was a question last time, what are quantum primitives? And I hope by the end of today's session, you will better understand what are quantum primitives and you will implement them by yourself with some nice examples. So what you will be gaining by the end of this session today. So first, you understand the difference between circuit synthesis or compilation and transpilation and why compilation is more beneficial. Now, this is a topic from the first session. I want to touch on a few things following the homework assignment that you had and following some questions from the Discord channel. So we'll start with this. Then I want you to understand what are the swap test and the Hadamard test, including some hands-on implementations that you will be doing in today's session and also in the homework assignment. And you understand when to use these quantum primitives. So these will be the first two quantum primitives we'll see. So quantum primitives are some, let's say, small or a common quantum algorithm building blocks. So they usually are used as part of a larger quantum algorithm. And today we'll see an example. And I want you to understand today when we want to use these specific two quantum primitives. So let's start with key insights from homework 1. And we'll discuss on the topic of compilation with transpilation, following many questions we had in the Discord chat. So this is a great work and great homework submission done by Christina Radian. So very well done for the homework assignment that you've submitted. And now I'm showing you part of what she has submitted. So these, if we're going back to the homework assignment of the first session, you had to model a multi-control node with 5 control qubits and 1 target qubit, and then to synthesize it for minimal width and then for minimal depth, and then somewhere in between. So here we can see 2 types of circuit implementation of a multi-control node. So this is a common building block or common, let's say, gate or algorithmic function of quantum computing. The first one uses 6 qubits, so 5 control qubits and 1 target qubit. This is the minimal number we can have for this kind of implementation, and we see this is optimized for width. Now, the second time, we optimize for depth. So we want to have a minimal circuit depth. And for this, there are more qubits that can be used. And the synthesis engine of Classiq automatically determines that the further qubits can be used in order to decrease the circuit depth. So here we can see the examples, and we can see that the underlying circuit implementation is completely different. Right, so here we can see one type of implementation on the bottom, and on the top we can see another implementation. Of course, she chose to show and demonstrate specific hierarchy or specific level of the hierarchy of the circuit implementation, and both this gate and this gate can be further decomposed into 1 and 2 qubit gates. Now, this is something that I wanted you to do at home, and then it gives you the first examples you coded hands-on, what's going on with taking a high-level description of a multi-control node of some quantum algorithm, and then synthesizing it, compiling it into low-level circuit implementation. Now, there are many questions about what's the difference between transpilation and compilation and synthesis. So I will walk through a small example that I hope will help you understand it better. So here I have some quantum algorithm. So I initialized 1 qubit for a quantum variable x, then I apply some Hadamard on x, then I apply the function called Eden. I don't tell you what this function is doing, but this is a quantum function that I apply on the quantum variable x, and then I do the inverse of x, okay? So the quantum program circuit that I will receive will be like this. So I have a Hadamard, and then I apply the Eden. So this is the function Eden. I called it Eden, and then I apply the inverse of the function. Now I'm telling you that the function implements x, so the NOT gate, and then Hadamard. So this is actually what's going on in the quantum program circuit, right? So I have Hadamard, and then I have xh. So this is the function Eden, and then I have inverse Eden, so it's hx. And this is the underlying quantum program circuit. However, the transpiled circuit is just a Hadamard gate, right? Why is that? Because two consecutive gates, or two consecutive Pali gates, we can cancel them out. So Hadamard after Hadamard is like the identity, so they are canceled out, and then we are left with x followed by x, and then we are remain only with the Hadamard gate. So I hope this example clarifies what's the difference between the quantum program circuit and the transpiled circuit. So the quantum program circuit retains the functional hierarchy in the circuit, as we've seen here, right? So we start from the functionality that we want, and then we can zoom into the low-level circuit implementation on the bottom figure, but it retains the functional hierarchy in the circuit. On the other hand, the transpiled circuit is the circuit of further circuit optimization. So as we've seen in the example, we could cancel out two identical gates that are consecutive applied on a specific qubit. And this is some further tweaks, some further optimization we are doing on top of the circuit itself. So these are the difference between the quantum program circuit that we can view on the Classiq visualization tool, using the Classiq visualization tool, and the transpiled circuit. And we have both information, the information of both. So the number of qubits will be identical in both, but the transpiled circuit can further optimize the circuit itself with some simple tricks, or like common tricks, like canceling two consecutive Pauli gates. Now, in part B of the homework assignment, I ask you to do sort of the same, but for a multi-control NOT with 20 controls and 1 target qubit. Now, Christina took it one step further, and this is a very nice graph and a very great work that she's done. So what are we seeing here? On the x-axis, we can see the width, the number of qubits used for the specific circuit implementation of the 20 control and 1 target, the MCX with 20 control and 1 target. So this is how many qubits we use. Now on the y-axis, we can see the circuit depth or the total gate count. So on green, we can see the total gate count that we use, but for now we'll focus on the program depth. So this is the quantum program that retains the functional hierarchy, and on the transpiled circuit depth. So we are focusing on the blue graph and on the red graph. What the synthesis engine, the compilation, what it enables us to do is to go from an implementation with 22 or 21 qubits to go to use some auxiliary qubits, to use 30 qubits instead of just the minimal number, and to reduce the circuit depth by this amount. Transpilation, what it allows us to do is for a given circuit width, so for a given number of qubits, we can further optimize the circuit depth. Now, let's understand what is more beneficial, or how beneficial is each one of the steps. So with compilation, when we go from this implementation, let's say with 22 qubits, and the circuit depth is roughly 2,500 or 2,900, I don't remember the exact numbers, we can use more auxiliary qubits, and the goal here was to optimize for depth. So we can use 8 more qubits and to reduce the depth by 29 times. So it's like almost 30 times improvement, which is super significant. Now, this is allowed only from the fact that we started from a high-level description of the algorithm, high-level description of the multi-control NOT, and then we synthesized it. We compiled it into a circuit implementation. And during the compilation, during the synthesis, so Christina asked the synthesis engine to compile it once for 23 qubits, for 24 qubits, etc., until 30 qubits, and to optimize for depth. Now, this, when we enlarge the circuit width, we are able to shortening the circuit depth, and we get a substantial reduction in circuit depth, which is most of the time the thing that we are interested in. Now, in transpilation, we are going from the program depth to the transpiled program depth. So this is this reduction, and we receive a reduction of up to, let's say, 2 times reduction in circuit depth. So it depends on which vertical line we are looking on, so on how many qubits. But these are the numbers that we can understand in terms of the reduction in circuit depth that are enabled by compilation or by the synthesis engine on one hand, and by the transpilation on the other hand. So now we can understand the difference between transpilation. So this is once we are given a quantum circuit, we can further tweak it, further optimize it. And the compilation is taking a high-level description, or the synthesis operation, taking a high-level description of the algorithm, of the model that we have. So for example, to have an MSIN X with 20 control and 1 target qubit, and then to create some underlying circuit implementation of it. And this is where the vast majority of optimization can be done. So here we can see that we received, for this specific example, a reduction of almost 30 times compared to 2 times reduction. And just to elaborate a bit more, the MCX is a key ingredient in many quantum algorithms we have. So for example, in Grover algorithm, most of the oracles that we uses MCX within them. So this is the reduction in circuit depth that we receive only for one MCX. Now imagine how efficient more we can make the implementation of our algorithm if we use a synthesis engine and we have many MCX within our algorithm. So this is a substantial improvement that we can receive. So well done for Christina for this homework, and thank you. It was really helpful in describing the differences and the advantages of synthesis and the differences between compilation and synthesis and transpilation. So now we will continue for the next step. So for the swap test. So we covered the key insight from homework 1 and discussed previous topic. Now we're starting the new topic of today. So we first discuss the motivation of the swap test, explanation on what is it, and some implementation, hands-on implementation. So the motivation, what the question we have when we address this and we're trying to come up with the swap test is how close or similar two quantum states are. And this is especially useful for quantum machine learning tasks, and as we will cover shortly. But the question you should have in mind is how close or similar two quantum states are. This is what we are trying to understand. And the swap test is a method, a tool, an algorithmic primitive that enables us to answer this question. So the definition, we have an input. The input is two quantum states. Let's call them psi and phi. And the output is the fidelity of psi and phi. So this is a measure of how close, how similar psi and phi are. So this is the definition, the overlap between the two, and this is what we receive. So this is a measure of how similar, how close these two quantum states are, and shortly we will discuss some further intuition of and limiting cases. But let's start with the algorithm itself. So we are starting with phi and psi. And then we have additional qubit. So we have additional test qubit that we are using. We apply the Hadamard, gate on this additional qubit. And now we are applying the control swap. So the Hadamard on the zero state, we receive the plus state. So it's equal superposition of 0 and 1. Now let's call it in the 0 branch, we do nothing. So we do not swap the two gates. The two states of psi and phi, and then in the 1 branch, or in the one, according to the amplitude of 1, we do swap phi and psi. And then we do Hadamard again. So we want to apply these destructive interferences that we used in the control swap. So this is another Hadamard gate. And then we measure. So it's quite simple, quite straightforward. So we have the two states that we are interested in. We have additional qubits that we are using along the way. We initialize it with the Hadamard, so we have an equal superposition of 0 and 1. Then conditioned or controlled by this qubit, we are applying a swap. So swap, it's swapping, just changing the state of psi and phi. So if it's 1 qubit, so it's just swapping the qubits. If these states are implemented by multiple qubits, so it's a bitwise swap. So the first qubit of phi is changed or swapped with the first qubit of psi, and so on and so forth. And lastly, we apply another Hadamard and we measure. What we receive is that from the probability of measuring the zero value of the test qubit, we can extract with this simple formula the fidelity or the overlap between these two states. So we measure the first qubit, we receive the probability or the histogram of 0 and 1. We take the probability of measuring the first qubit 0, multiply it by 2, decrease 1, and we receive this fidelity, this overlap. And this is really nice because it's quite simple, very, very useful tool, and quite straightforward. So this is quite nice. Now let's try to develop some intuition for this swap test. So if the states of psi and phi are identical, right? So if they're identical, their inner product is 1 because they're the same state. Now the probability of measuring 0 will be 1, right? So we have here, we'll have 1, and then probability of measuring 0, we'll have 1 as well. So this is one extreme. Now, if they are completely orthogonal and their inner product is 0, then the probability of measuring 0 will be 1/2. So these are the two limiting cases. And we can see from here that we won't receive something smaller than this 1/2, because we take the inner product and modulus square. So the minimum value that we can receive for the probability of measuring 0 will be 1/2. And these are the two limiting cases. So again, we want to understand how similar, how close these two quantum states are. We receive as input these two quantum states. We initialize another qubit as auxiliary qubit, as the qubit that we calculate this overlap. Hadamard on this qubit, control on this qubit, control swap between the two states. If these are 1 qubit states, so just swap between the two. If there are multiple qubits, so bitwise swap. And then another Hadamard, measuring, understanding what is the probability of 0, and then one line of post-processing, and we'll receive this fidelity, the overlap, how similar these two quantum states are. So let's discuss about, let's say, we can call it a canonical use case for this. So here we have a general unitary, which is parameterized. So we have some parameters in this unitary that we want to optimize according to something. Now we have here the unitary that initialize the quantum state of psi. So here we have the state psi, and here we have some unitary that we want to make as close as possible to the state of psi. And later on, we'll see a more specific example from paper implementation. What we can do is to have this swap test in order to optimize the parameters of this unitary that they can do a state preparation of psi, or as close as possible. And from this, we can calculate the overlap, the fidelity, but it depends on the variables that we have in this unitary, right? So these are the result that we receive is a function of the variables, the function of, let's say, theta. Theta can be one variable or a vector of variables, classical variables. Let's say these are angles of rotations or further variables, unknowns that we are trying to optimize. Now we take this result and we're trying to maximize it. So the goal here is to create this unitary with parameters that will be as similar as possible to the unitary that prepares the state psi. So we have these parameters, we have this is a well-known unitary. Now we're doing the swap test. We're trying to maximize this overlap, this fidelity. It's parameterized. Then we are classically optimizing over the parameters of theta to maximize this. And then we receive a new set of parameters. We insert these new sets of parameters into the unitary. We calculate it again, and then we optimize it again. And we are doing a loop here until we are converging to something that is either a local minima or something that is meaningful. So this is sort of the canonical example, how we use it. Now the question is, why should we do it? How we do it? What are the variations that we can do? But this is a common structure that we can use the swap test for. So we have some unitary with parameters unitary that we want to create some states that we know what the state is, but we don't know how to prepare it. So okay, here it's a bit of cheating, but the cheating is only for training this specific unitary, and this is the way we are doing this. So I think through examples it will make it clearer, but this is the high-level scheme, the high-level canonical example of how we use swap tests in quantum machine learning or variation hybrid algorithms in quantum computing. Now, further examples, this is also a paper that uses the swap test, so quantum fingerprints, and this is a famous paper, so I encourage you to go over it, to skim through, and to try to spot where they use the swap test within it. And this is an example that we'll cover briefly, so quantum autoencoders for efficient compression of quantum data. So this is another paper, a research from the field of quantum machine learning and hybrid algorithms. Now, within the paper, we can see this figure. So let's try to understand it more according to the scheme that we have discussed in the previous slide. So here we have some general unitary, and we have some parameters. And then we take some of the output of this unitary, and this is what we are trying to optimize. And we have a reference state. So this is the state that in the previous slide I showed as U of psi. So we prepare a reference state somehow, and then we are doing the swap test. So we want to make this state that comes out of the unitary as close as possible to the reference state, and we measure how close they are using this swap test. We measure the overlap effectively. We do some post-processing, and we compute the cost function. So the cost function is from the probability of 0. We can calculate what's the cost function, what's the overlap, or what's the fidelity, and then we can maybe have some further cost function. And then we apply some optimization scheme on what we receive, and we receive from the optimization new set of parameters, and then we are doing this loop over and over again. So this is an example from this paper. You can search for this paper on arXiv and then go through it. But now when you approach this paper, you have the ability to understand some parts of it. And this is one of the key enabling points that quantum primitives enable you, or the key advantages of understanding and learning in depth and really understanding implementation and the theory and understanding the whole picture of quantum primitives, is then you can come to new quantum algorithms or to new papers and decompose these new quantum algorithms that you see for the first time into those primitives, those quantum building blocks, and further understand what's going on. So now I expect you, after the end of this session, to come and to see one kind of this algorithm. Okay, so maybe you won't understand everything here, and overlap or the fidelity, you don't fully understand it, but you have the rough idea, and how to apply the optimization, you might not fully understand how to do it, but you can view on the circuit, you understand that here are some parameters, here is the swap test, we are trying to understand how similar the output of this quantum state is to this reference state. So these are the words that we understand. So now you have the ability to understand some set of papers, of really state-of-the-art papers that use this swap test. Now, by the end of the full program that we'll do, you will acquire more and more quantum primitives, and I hope this will span a large variety of quantum algorithms, of state-of-the-art quantum algorithms that you will be able to understand and then to develop by yourself new quantum algorithms. So this is why quantum primitives are so important to understand, and I think this is the best way of learning quantum algorithm in general and advanced quantum algorithm specifically, is to understand the building blocks, the quantum primitives of the algorithm, and not to review the hundreds or thousands of different or variation of quantum algorithm we have. So this is a tool set that you will receive. Now let's try to have some critical thinking about it. So I encourage you to think why to use the swap test and not just to measure the two quantum states, right? So we can do some quantum tomography to measure the state of psi, to measure the state of phi, and then to calculate post-processing and just do it this way. So I encourage you to think and maybe to search a bit. Why should we do it, and when should we do it? When we'll do tomography, or if we'll never do tomography, but try to understand why we should do and we should use this swap test and not a different option. And another important thing is how many measurements one needs to do for achieving desired accuracy, right? So, and this is something that we'll touch in the hands-on part, but obviously if we measure with one shot, we won't receive anything because the probability, we need to acquire more shots in order to have a reliable probability. But what does it mean reliable probability? It depends on what is the accuracy that we want to achieve. So it is some connection between the accuracy we want to achieve of this overlap between the states and the number of shots that we need to measure. And I encourage you to think and to try to understand what are the relation here. And when you approach or when you review some papers, you need to think, okay, it's not enough just to have the swap test. If it depends on other things, so we need to understand the whole picture. So these are 2 points that I want you to have in mind when you think and you view and you further analyze and research the swap test. So this is a very useful tool. You can understand further research papers and more research area within quantum machine learning. And there are some points that you need to consider when you want to use it or when you view or read other papers. So this is a good time for questions, and then we'll move to the hands-on implementation part. But if there are some questions on the theory part or why you should use it or anything about the swap test, so this is a good time for having the question.
Just as a reminder, the questions are to be posted in the live questions channel on Discord. So I'm seeing a lot of questions posted on general questions and some other quantum algorithms channel too. If the questions are related to this particular session, I would advise everyone to bring those questions to live chat so we can track everything at once. Quick question, is it possible to perform finding Hadamard matrix on Classiq?
I'm not sure what is meant by the Hadamard matrix. There is the Hadamard gate, and anyone can use it with the Classiq platform with the simple syntax. If one wants to further explain, so I'll be happy to answer.
Yeah, so Ira from Indonesia, if you could just clarify your question a little bit further in the chat, that would be awesome. Another question from Parsa from Iran. Is it possible that repeating the swap test doesn't converge to a single optimized state? And if so, what does that tell us about the state?
That's a good question. So if we repeat, so assume that measuring many times, so having a large number of shots, if we won't converge to the desired state. So yeah, this is possible. Let me go back. Okay, so here we can see in this example, they have the reference state. Now, they don't explain how they initialized or how they prepare this reference state. Now, for a general quantum state that we want to prepare, we have many parameters. So we have, I don't remember the exact numbers, but for a general unitary, you have many parameters that you need, or many degrees of freedom in the Hilbert space that you need in order to create a general reference state or a general state. Now, usually what we are doing is we have some ansatz, we call it, some parameterized quantum circuit that we don't have the full degrees of freedom to span the entire Hilbert space of the number of qubits that it applies on. So we have effectively what we can do is we span only a limited space or a subspace within the Hilbert space of the full Hilbert space of the state that could be theoretically spanned. And this is usually done because it's more efficient to use fewer parameters. Now, the swap test, it will, in this case, will enable us to converge only to the closest point we can have to the general state. So it's highly possible that we won't span the full Hilbert space, and the reference states won't be in the subspace that we span with the general unitary, with the parameters. And then we won't be able to come as close as we want, but we'll be able to come as close as we want within the subspace. So this is a general thought on this example. And also within this, there are the issues of how we can converge and how we optimize, and are we in a local minima or a maximal minima, and then there are further things. But you should have in mind that not always, or most cases, you won't be able to converge to the reference state exactly. That's a good question.
Okay, thank you, Adam. Another question is from Mohammed Reza from Iran. He asked that, is it possible to deconstruct a unique setup based on different combinations of primitives?
Is it possible to construct a unique setup
based on different combinations of primitives.
Okay, so I'm not sure what is exactly meant in the question, but in general, now that you will view, or after the course that will finish, when you will view and implement and review some algorithms, you will have the ability to understand how they can be decomposed into different quantum primitives. And each one of them, it's not just that we are taking the quantum primitive as is and plugging together. So there are some nuances revolving this. So I'm not sure what's the question, but it's not that there is a list of, I don't know, 10 quantum primitives, and then we can do all the possible combination of these 10 quantum primitives, and we'll span all the algorithm in the world. So I think it's a bit more subtle than this. And you need to remember that also when we speak about this quantum algorithm, this is one part of a general quantum algorithm. So for quantum algorithm, we can decompose it into 3 steps. So we need first to encode the data. Then we evolve the data. We actually implement the algorithm, the quantum circuit, the quantum algorithm using the quantum circuit. So this is how we evolve the data, and we need to do it in a smart way. And then we need to measure and post-process. So the first step and the last step are not really related to quantum primitives. So there are also primitives regarding how you upload the data, you encode the data into the quantum circuit, and how you measure and post-process. But what we are dealing with in this course, and I think the common thing that we think of when we speak about quantum primitives is regarding the main step, which is evolving the quantum algorithm on the quantum circuit. So I hope this clarifies the question.
Okay. One final question before we move forward, and this is coming back to the question which Ira asked on doing research on Hadamard case. So a little background on that. Ira asked that finding a Hadamard finding a Hadamard matrix among the set of binary matrices for corresponding order is a hard problem. So this is a question more on time complexity, and this particular problem has a potential to be solved on quantum machines, or particularly quantum annealing machines. Can that same routine be somehow replicated or done on Classiq systems?
So that's a good question. So if it's something that relates to quantum algorithms, so definitely we can do it using Classiq, and I'm happy to take it offline and further explain and see together how we can make it.
Perfect.
Great.
Okay, and move forward now.
Thank you. So now we'll move to the hands-on implementation. So I encourage you now to open, or ask you now to go to the docs.classiq.io to the documentation, and within the explore page, you have the swap test algorithm, and then you can also review what's going on in the tutorial, but you can open it in the IDE. And then once you open it, we have some set of questions that I encourage you to do along the way. So I can share my screen, and I want you to go to this page. So you can do it from the documentation, from docs.classiq.io, go to the algorithms and then the swap test, or you can go from the Classiq IDE to the model, and then you have algorithm and swap test. So these are the 2 options that you can access this page. And now, as you can see, we have a pre-built function of swap test within the Classiq platform. So this is a primitive that we already implemented for you. You can also implement yourself, and you can call the function mySwapTest, for example, and then to implement, and I think it's a good exercise, optional exercise to do by yourself. But now I want you to go to this page, and we will have some tasks I want you to do here that will help you to understand what's going on. So I'll let you do it for a second. And then you can view the exercises on the Canvas platform, and you can also view it here. So what I want you to do is to use the pre-built example of the swap test from the IDE. So this is what I opened for you, and adapt the 2 states to be 2 qubit states with 0 overlap. So to be orthogonal states. And I encourage you to use the prepare state function for this use case. So use a standard error bound of 0.01, so you can view what is the arguments that you should enter into prepare state, and we'll do an example. But what I want you to do is to prepare these 2 states. First, prepare 2 states with 0 overlap, and then I want you to synthesize the algorithm and execute using the Classiq simulator, and we want to understand two things. So what was the probability of measuring 0 in the test qubit, and is it as you expected? So there is the theoretical argument of what we want to achieve from the swap test. And what I want you to do now is to go through it. So I can start and show you some things we want. So first, we want to do the prepare state. So we use the prepare state, and this is the syntax that we use. So first, we want to prepare state on state 1. So we want to prepare the state on the prepare state of this qubit array. Now, let's say we want to prepare the state 1, 0, 0, 0. So this is a 2-qubit state. And the second argument here should be the error bound. So we won't dive into too much details here, but when we are doing a prepare state, so this is a function that does a prepare state. So we have the desired state. So here we have a desired set of probabilities, not amplitude, probabilities that we want to have. So we want to have full probability or probability of 1 measuring the qubit array state 1 in the state 0, and then 0 for measuring it in all other states. And the error bound is how the prepare state function, what is the gap or the functional freedom that it can use in order to make it as accurate as possible. So usually when we want to do something more accurate, we need larger circuit depth and more resources. So this is how many resources we need. And you can ignore it for now and just use the 0.01. Now let's do an example. So I can copy and paste this, and I'm going to do state 2. And now I prepare the two states to be identical, right? So I prepare the state here and prepare the state here, both to be identical. And I'm using the swap test. So I don't need to understand now how it is implemented the swap test. I can just use this function, this quantum primitive, and then I can synthesize it. Now we can view what's going on here. So I can view the circuit. So I have one block of state preparation, another block of state preparation, and the swap test. Now the swap test receives state 1, it receives state 2, and it also uses a test qubit. Now we can zoom in and understand the swap test, right? So this is exactly how we thought it should be. So we have the Hadamard, and then we have control swap. And the control swap is bitwise swap. So we have a control on the first qubit of each state, so of state 1, and we are doing control swap on first qubit of state 1 and first qubit of state 2, and then we're doing a control swap on the second qubit of state 1, the second qubit of state 2, another Hadamard, and we finish like this. So this is what I want you to do, and then I want you to execute and to run it on a simulator. So this is the first exercise, and now if I share the slide again, so I want you to go and over what we did now, to use the previous example of the swap test from the IDE, adapt the two states to be 2-qubit states with 0 overlap. So what we did now is not 0 overlap, and you can think, so 0 overlap are 2 orthogonal states. Now we did something different, and use the prepare state function, and I want you to run it, and to understand what was the probability of measuring 0 in the test qubit, and is it as you expected. So this is the exercise, and I can go back in a second and show you the formula that we wanted to have and how we calculate the fidelity from the 0 probability, but please do it alongside. So now we have sort of a roughly 10-minute session of hands-on, or 5 to 10-minute session of hands-on, and just for you to acquire the more capabilities of what is the swap test.
Eden, would it be possible to just go back and walk the participants through the code? People are trying it hands-on, so they have fallen a little back on trying to keep up with everything that's going on.
Yeah,
also,
sure.
Another question. For some of the participants, the IDE comes with, it's already populated with prepared amplitudes. So can they safely remove that stuff before trying this out?
So sorry, if they can use the prepared amplitudes instead?
yeah, for them, the IDE already has prepared amplitudes. Should they remove that before doing this, or
Yeah.
should we just keep it as is and continue with this code?
Yeah, so if we press on the swap test, we have some example here, and we should follow the tutorial in order to understand this example further. So if I'm going to docs.classiq and I'm going to explore, and then I'm going to algorithms, and I'm going to the swap test algorithm. So this covers the example that we have. So this is the Python code of the example. And we can see how it is prepared with the Python. And first thing, I encourage you just to open this swap test with the prepare amplitude, as you said, to synthesize, to view the algorithm, to understand that everything runs smoothly on your computer, that you know how to synthesize, to run, to view the circuit, view that you have the swap test, and then to continue to the next phase. Here we can see that we are preparing a state with 3 qubits, not with 2 qubits. We are using the prepare amplitudes instead of the prepare state. So this is a more complicated example. So yes, to answer the question, what the participants you will need to do is to delete these 2 lines, and instead of prepare amplitudes, to have prepare state of state 1 and prepare state of state 2. Now, if I'm bringing back the code from earlier, so the only thing from these 2 lines now that I have on the screen that the participant should do is to change the prepare state of state 2 to some state that you're orthogonal to state 1.
Sure, right.
Are there any further questions that I can answer meanwhile?
Yeah, no questions as of now. Okay, there is one. Yeah, this is a little bit earlier from the session, but is the U, capital U theta, the parameterization unitary is to check how psi is oriented towards the angle theta.
Okay, so can you repeat the question? So we had, I will go back to the slide, and we had here.
Right. So the question is that does theta, the parameterization unitary, check how psi is oriented towards the angle theta?
Yeah, one can think about it this way. We need to remember that psi is a quantum state and theta is a classical vector of parameters. So with this scheme that we see here, there is some connection, or we can have some mapping between each classical vector of parameters theta and the quantum state psi that implements it, but they live on different spaces in the mathematical world. So this is a quantum state that is part of the Hilbert space of the specific number of qubits that is spanned by, and this is a classical vector of parameters, and they can be real parameters or complex parameters. There can be different dimensions between the vector parameters and the psi state, but as we can see here, each vector of parameters creates or is connected to psi 1 quantum state psi.
Right. There's another question. Archit from India asks, if you already have prepared some state phi, why do we need to use a parameterization circuit or a variational circuit to create that like an identical state again?
That's a great question. So let's see if we can understand it from this example. Not exactly. So many possible answers. One is that usually we are not interested in actually being able to do it again. Or that's not exactly true. One is we can find a more efficient way to implement psi. So as I said, And usually we need many degrees of freedom in order to implement psi. And maybe we can find some shortcut that we can use in other quantum algorithms that we implement psi using fewer number of parameters. So a smaller unitary that will create almost the same state psi. So this is one possible answer. Another possibility is that, okay, we know the state of psi, but we want to have some family of states. So not the specific psi, but maybe some family of states. And we want a unitary that will prepare this family of states. So we can optimize over the parameters using psi, and then optimize over the parameters for another state, and then find some logical mixture that will span a wide range of states within a given family. So this can be another direction. So several aspects. And then in the quantum multi-encoder, so this is another example. I encourage people to go through it. I'm not too familiar with the specific implementation here, but again, here we can see that the reference state will have, in general, have some many degrees of freedom. And here, probably what they have here is a limited set of parameters that they optimize for. So it's not necessarily that they have a perfect overlap between the state that they prepare with the unitary U and the reference state, but they will try to get as close as possible using fewer number of parameters. That's a good question.
Wonderful. I think the participants are now trying that on their own, and some of them also shared some histograms and are asking how to interpret the histograms on the Discord chat.
Okay, that's a great question. So I can see from, let's go back to the platform. And if we execute and we have, let's say 100 shots. Now we can see here that there is a perfect overlap. Now we can change on the filters from counts to probabilities. So here we can see the probability. Now I see in the chat there is a histogram with 517. So I encourage you to use the filter and change it to probability, and then you can understand it as probability. And the formula for connecting the probability to the overlap that we want to receive is this formula. So 2 times the probability minus 1 is the overlap that we are trying to extract. So you have the formula also in the exercises on the canvas, but this is the formula that we want to have. And from the measured probability, we want to extract or to do this small calculation step. So you don't need to finish all the 3 exercises now, but on the high level, I want you to do the first exercise with orthogonal states. So we covered one different aspect. So we covered exercise 2 actually. So we repeated exercise 1. So we started exercise 1, but we adapted the 2 states to be 2 qubits with perfect overlap, right? And so what we did is that we prepared the state, and we prefer the 2 states to be identical. So we prefer 2 states to be the 0 state effectively. And then when we measure them, we receive probability of 1 being in the 0 state, and 2 times 1 minus 1 is a fidelity of 1. So this is what we expected because we created a state that is perfect in that sense. So I can give you a hint. So let's say if we change it to this state, so you should think what will be the value. So will it be something that is with fully orthogonal, so the overlap will be 0, and what is the probability in this case? And you can also try to think if you prepare probability of 0.5 and 0.5, so there is some maybe overlap between the 2 states. So I encourage you to play around and to connect what you measure with the probability to the value that you receive here. So this is what I expect the participants to do. Now, we can continue to the next phase. Or Vardaan, do you recommend having a few minutes break, or should we continue to the next part?
Yeah, let's just have a couple of minutes for the participants to try. They're still trying to catch up with the online ID and running the circuits.
Perfect.
Yeah, sometimes I understand people having a hard time to catch up with a live lecture. So if it's absolutely okay if you're not able to do all three just yet. You can try with the first exercise, and if there's something left, you can go on to the YouTube recording later on and complete the exercises.
Yeah, definitely. The reason I want participants to start and implement throughout the lecture is I think when we are trying to actually code a quantum algorithm and an algorithm in general, we really understand it. So there is one thing to understand it in theory, but when we need to hands-on do and implement it and execute and analyze the result, this is a completely new thing. So it's even if not, if participants won't be able to finish all the exercises, and even if not to finish any exercise, just the effort of trying to code it raises many questions that clarifies the understanding of how to do it. So what are the states? What is a quantum state? How we prepare them? What does it mean in overlap? So I think these terms and these ideas are becoming way more concrete when we actually try to code it in a specific way. And I think the Classiq platform is very useful for this because we can quite intuitively and easily experiment with the IDE. We don't need to raise a Python or to install a Python environment and to do something more extensive. So throughout, when we have ideas, we can use the IDE to experiment and to go over the things.
Perfect. And for all the participants who are doing this right now, I would advise you to keep on sharing your final histograms on the live chat so everyone is aware that you are performing and you're getting the results. And it also gives us a sense that, yeah, people are, doing it correctly. Another question for you, Aiden, is on, does Classiq use an ancilla-free swap test?
An ancilla-free swap test. I'm not sure what is the ancilla that is referred here. So as we've seen, so in the swap test, we have the test qubit or the overlap qubit that we use. We can think about it as an ancilla qubit, and then we have the two states. So I assume the question is if we can have some swap test without using this additional qubit. I don't think it is possible in general. So it doesn't. It's not related to no. So we need to do this control in a control way, and we need at least one additional qubit in order to do so. And if we don't have this additional qubit, so there is no option. So in this regard, this quantum primitive doesn't require a lot of playing around between, or there are not so many different implementations. So there is, for this quantum primitive, there is one implementation. It's straightforward, and we use this implementation in other or this primitive in other algorithms, but there is no too much of a thing to do here. Beside the fact that the control swap, might be multiple implementations within the control swap.
Right. And from the histograms and the images shared on the Discord chat, I understand that most participants are doing it correctly. If they are receiving 100% probability for the zero state, I think that is good. And then if you change it to an orthogonal state, then the probabilities should also change, right?
Yeah, definitely. So the overlap, the overlap is 2 times the probability of measuring 0 minus 1. So if the probability of measuring 0 will be 1/2, so we receive the overlap to be 0. And then if the probability of measuring 0 will be 1, the overlap will be 1 as well. So these are the two extreme cases that we covered at the beginning. And then there are middle cases of understanding between 0 overlap and between 0 fidelity and full fidelity or completely identical states.
Perfect. Okay, yeah, I think we can move forward now.
Perfect. So I encourage the participants to continue after the lecture to play around and to get a feeling or a proper feeling of what is the swap test and to see the three different cases. And I think this is a bit more challenging part to create the fidelity of zero. So you need to think what to do with this 2-qubit state. But I'm quite certain that the participants will be able to do it after a few minutes of thinking. So we will move to the next part of the session, the third and last part of today's lecture, and this is the Hadamard test. So this is another quantum primitive. It's, let's say, a close cousin of the swap test, and we'll start with the motivation, explanation, and for this test, we will create, and I'll do a live demo how we implement this Hadamard test, and this will be the foundation for the homework assignment that you will have. So what is the motivation? What is the question that we are coming when you want to understand the Hadamard test? Is how to evaluate the expectation value of a given unitary matrix for a specific quantum state. So even this question is super fundamental in quantum physics in general and quantum algorithm computing in particular. So we are given many unitaries, and we are dealing always with unitaries, and we have the quantum states. And the first thing, or one of the first things that we actually want to do, is to evaluate the expectation value of a given unitary that we implement using a quantum circuit for a specific quantum state. So this is really, really a fundamental thing that we want to achieve. Now, what is the standard way of calculating or evaluating expectation values? Usually we decompose the unitary into a sum of Pauli strings. So I'm covering here a flow that is common. Sometimes it's swept under the rug when we are dealing with quantum algorithms, but it's really fundamental to understand what is the standard way to do it. So we have a general unitary, and the Pauli operators or string of Paulis, they span the entire unitary that we can evaluate. So we decompose a given unitary into sum of Pauli strings. So in one dimensional with 1 qubit, we can decompose it to X, Y, Z, and identity. And then with 2 qubits, we decompose it to some Pauli strings. So let's say XZ, and then II, and then IY, and so on and so forth. So we span the given unitary on using all the Pauli strings. Now we express each Pauli in the standard basis using a change of basis transformation. So what does it mean? At the end, with quantum computers, we need to measure only in the standard, or we are able to measure in the general framework only in the standard basis. So for measuring the standard basis, we need to express all the Paulis that we have using the Z Pauli and the identity, because these can be extracted in post-processing from the standard basis measurement. So we need to do some transformation. So for example, the X Pauli can be expressed using transformation with Hadamard, Z Hadamard. So we do some Hadamard transformation, and then we, in this other basis using the Hadamard, we apply the Z, and this is the X Pauli. So we need to apply for all the Pauli strings, and for the Y operator, there is a different transformation that we need to do, but we need to express everything in terms of Z and identity in the middle, using the transformation. Now, after we express, so this is a mathematical way, we need to apply the transformation. So we actually apply, for example, here, we apply a Hadamard gate on the state in order to measure, and then after we measure in the computational basis, we can extract it. So the next step is to measure independently each non-commutative Pauli string. So this is a subtle point, but at the end, when we decompose the unitary, we can receive a sum of Pauli strings. So for example, we can receive a unitary that is implemented with on 1 qubit with X plus Z. So these are not commutative, and then we need to measure 2 times, and for each measurement, we need to do multiple shots. So we need to measure independently each non-commutative Pauli string, and then we need to post-process the result in order to evaluate the expectation value. So firstly, I think this is good to know in general, because this is the standard way of how we actually evaluate expectation values on quantum computers, and this is a topic that's swept under the rug, but it's quite complicated, we can say, and there is some nuances, and we need to do this decomposition and transformation, and it can be quite expensive, both theoretically and implementation-wise. Now, the Hadamard test is another way, or maybe a shortcut, to actually evaluate this expectation value of the state. So this is really nice. Now, the 5 steps and everything that I covered earlier, for now, you can forget it. You should remember or understand it later, but the Hadamard test will give you a shortcut how you can do it in a straightforward way. So the input is a quantum state psi and a unitary U, and the output is the real part of the expectation value of the unitary U with the state psi. Now, there is a variant of the algorithm that we can calculate the imaginary part as well, and then we can evaluate the expectation value in general, but the standard way is to evaluate the real part of the expectation value. How we do it? So we start with the state psi, and then we have one additional qubit. We initialize the qubit with Hadamard, and then we apply a control unitary. So we are given the unitary, we just need to apply the control unitary. We're doing another Hadamard, we measure, and from the measurement, the real part of the expectation value is 2 times the probability of measuring 0 minus 1. So as we can see, it's very, very similar to the swap test, and one can understand the swap test as a variation of the Hadamard test. But this is straightforward, and we are given the state psi, or we initialize the state psi, we are given the unitary, another test qubit, Hadamard control unitary, Hadamard, measuring and receiving the, or extracting probability of 0 and calculating the post-processing. So this is very nice, very useful, very intuitive compared to the 5 steps that we did earlier. There is only the subtle but the significant challenge of implementing a controlled unitary. Now, this is the point where using high-level functional design is becoming super useful, because you don't need to think about the implementation itself. You are given the unitary, and in a few minutes, we will code and do a demo of this live. And then the implementation, the synthesis engine of Classiq, the compiler, transform this high-level modeling of controlled unitary to actual circuit implementation. And now we can view that if the unitary itself has further multi-control knot or MCXs, so it becomes very beneficial to use the synthesis engine, because you can tweak the parameters of maximal width or maximal depth and further optimize the algorithm. So let's develop some intuition and the extreme use case, the cases. So if the real part of the expectation value is 1, then the probability of measuring 0 is 1. So let's try to calculate here. So we have the real part of the expectation value. So this is 1. And then we understand, okay, the probability of measuring 0 is 1. Now, if the real part of the expectation value is 0, so this is 0, the probability of measuring 0 is 1/2. And if the real part of measuring the probability is -1, so the probability is of measuring 0 in the test or the expectation value qubit is also 0. So here, not as we had in the swap test, here we can also measure 0 in the test qubit. Now, in order to understand some examples, so I encourage you to go to the archive. So archive is the preprint that we have for papers in the community, in the physics community in general. And it's a great place to view and to read and to research for what's going on in the quantum ecosystem. So I encourage you to go and search over there, Hadamard test, and you can specifically search for the abstract. And there are 138 results for having Hadamard test in the abstract. Now, if you search for the full text, you receive many more results. So these are all papers, research papers, and you can filter according to the new papers or more relevant or anything that you want. But these are papers that are using this Hadamard test. So state-of-the-art research that uses this Hadamard test as if it's mentioned in the abstract, so it's in a key part of the algorithm. So now you have access, or after you understand what is the Hadamard test, you can now read 138 research papers. Many of them are super relevant state-of-the-art quantum algorithm, and this gives you another tool set of understanding what's going on. Now, this is one of the papers over there. I wasn't familiar with this paper before, but this is quantum error mitigation for Fourier moment computation. And this is the work done. Now, scrolling skimming through the paper, we can see these two figures. So the first figure, we actually see the Hadamard test, right? So we Hadamard, and then we apply some control unitaries. Here they have 3 unitaries. So we can think about this as a concatenation of unitaries. This is one unitary, another Hadamard. So this is from the paper. Now we can really understand, okay, this is a primitive. This is something that we can understand, a structure of the algorithm. And this is another variant of the Hadamard test. So here we can see that it's not exactly Hadamard control Hadamard. They have some additional gate. And I think I don't understand, and I haven't read fully the specific thing here, but I can, from what I know and I understand, this could be used to evaluate the imaginary part of the expectation value. So again, even if you don't exactly know and you don't research through the entire and read carefully the paper, that can take long, just for skimming through the papers and understanding the concepts, you can get a feeling of the paper. And I think this is also a really useful technique and tool when you want to review many papers, or you want to review a field or get a feeling of what's going on in the field. So you don't need to read in depth the papers in order to understand everything. You can skim through, and now that you can spot some primitives and some construct that you understand, it's very useful in understanding the bigger picture without diving into details. And then once you know what you want to read, so you can invest the time and learn it carefully, and this is super important. But the first phase is to have some intuition. So these are 2 figures from the paper, and already now you can have a feeling of what's going on over there. So let's go with the hands-on implementation. Maybe I will have a quick round of questions, so maybe 2 or 3 questions if there are some important questions, and if not, we will continue to the hands-on implementation. So Vardaan, if you feel that there are some repeated question in the chat, so I can stop for a moment, and if not, we can continue with the implementation.
Yeah, I think most of the questions, the participants have tried to answer them to one another, so that's wonderful. One question, the example which you just mentioned, was that done on the IDE by the participants themselves, or is it a preloaded example which they can just start working on, similar to the swap test example?
Okay, so now we will touch it, and no, this is not a pre-built example, and now I will code it live with the participant. So this is what we are trying to evaluate. So I'm continuing now with what we are trying to do. So we are trying to evaluate the expectation value of the quantum Fourier transform matrix. So this is a common matrix, a common unitary that we used in quantum computing, and we are applying the quantum Fourier transform. So for this, in Classiq, we can just write Q of t and then apply it on anything that we want to do. So we want to apply to evaluate the expectation value of the quantum Fourier transform for the 0 state using 4 qubits. So this is the task that we want to have. Now, this is the final circuit that we expect to have. So we want to have Hadamard, and then a control quantum Fourier transform, and then another Hadamard. And this is the code and how we'll do it. So I will go quickly through the logic that we have, and then we'll implement it together. So we can play around with the outputs, but what we will have is, first we initialize a qubit, which will be the expectation value. We initialize the quantum register psi that we will apply the QFT on. And then we use the within apply construct of Classiq. So you covered it in the Classiq 101, but we apply the transformation. So here, the within apply effectively say, okay, now we're applying the Hadamard on the expectation value. And this is the first act that we are doing. Then we apply some operation, and then automatically the construct know to apply the inverse of the action that we used firstly. So within applying a Hadamard on the expectation value, so it automatically says, okay, I will have an Hadamard in the beginning, I will have an Hadamard at the end on the expectation value qubit. What I want to do between these Hadamard, I want to apply a control. So controlled on the expectation value qubit, I want to apply the quantum Fourier transform matrix, or the quantum Fourier transform unitary. So now we will go to the to the part. So we will code it together. So I think it will give you more intuition of how we can do things. So first we have the main function. And what we want to have at the end, the output should be the expectation value, and it should be qubit. Now, first I want to allocate. So allocate is initialize. I want to initialize this expectation value qubit. And this is the syntax that we use. Now I want to declare, because the only thing that I'm interested as the output is the expectation value qubit. But now what I need to do as well, I want to have the psi quantum register. And I want to initialize this quantum register with 4 qubits. So in these two parts, I initialize the expectation value, and I have also the psi quantum array, quantum register that I declared here and initialized here. Now I'm applying the actual Hadamard test. So within, and then we'll have some action here, and then we have apply, and then we'll have another action here. So what we are doing first, and we want to apply the Hadamard on the expectation value, right? So this is the first thing that we want to do. So we apply the Hadamard on the expectation value qubit. And then what we want to do, we want to apply a control. So we have the pre-built or the construct of the QMOOC language. So control on what? Control on the expectation value. So what we want to do, controlled on the expectation value, we want to apply the QFT on the psi register. So this is what we want to achieve. Let's see if we have some errors or we can synthesize. So expectation value is undefined. So what does it mean? Let's see here. So we have here expectation value. Now it means that we have some error in the syntax here. So this is a mean indicative error message. So now we can see that all the expectation value are with the correct syntax. So thank you for the error message Classiq platform. And that's great, because now we can actually receive the implementation. So as we can see, we have the Hadamard, and then we have the controlled QFT, and then we have Hadamard again. So we can zoom in and understand how the QFT is working. But this is what we want to achieve. So first, I encourage you now to go and to implement it yourself. So I see there is a print screen in the Discord. I can also share the code, but I encourage you just to go over and to implement it yourself. So as I said, it's totally different to see an implementation and to implement it yourself. So even if you're just copying and pasting, try to play around and see that you understand what's going on the high level. Now, once we have the implementation, what I will want you to do, and now we are approaching the end of the session, so you will do it at home. So I want you to follow the implementation that we just did and code in the IDE, the Hadamard test for calculating the real part of the expectation value of the QFT unitary with at the state 0 with 4 qubits. So the first two lines we already did together. You have the code in the Discord chat, but I encourage you also to try to code it by yourself, maybe from the print screen, maybe from the recording, and it's a different thing. Now execute the algorithm from the IDE with 1000 shots and calculate the real part of the expectation value using the formula. So this is the general formula. So the real part of what we want to achieve is 2 times the probability of measuring 0 minus 1. And the question is it what you expect it to be? So you need to understand what is the quantum Fourier transform unitary and what should be theoretically the expectation value of the 0 in the 0 state. And a hint, should it be a real value? So we don't need to take the real part of the real value because it's already real, or it's a complex value and then we won't receive. So you should think about these things. And then I want you to repeat exercise 1, but now execute the algorithm with 2000 shots. So, and then you I want to ask you, is the result better? And better in what sense? Is it closer through the theoretical value? And then I want you to repeat it with 5,000 shots, and then to understand if it's better. And this touches on the point that I've discussed earlier. So how many shots and what is the convergence of the algorithm according to the number of shots we have and according to the accuracy that we want to achieve. So these exercises help you to start going through it. And then you have the homework assignment, which is a bit more elaborative than this. And in the homework assignment, you will show me what is the convergence. So you will show me, and what you need to do is to submit a graph, and everything is detailed over there, but to submit a graph of the same thing that we are doing here. So evaluating the expectation value of the quantum Fourier transform in the 0 state, and you will need to execute it, to run it with different number of shots. So one time with 1,000 shots, 2,000, 5,000, etc. So everything is explained over there. And then I want to see a graph of what is the value of this real expectation value as a function of the number of shots. And I want to add also the theoretical value, and to see and to understand if there is a relation, if we converge as we increase the number of shots, if there is a limit. And this is the assignment will answer one of the questions that we had earlier. So the question was, can we measure as many times as we want and to get closer as possible? And this will address this kind of question. So we have the implementation in the chat in the Discord. You have also in the recording that you can see the implementation. This is what you need to implement. By yourself, you need to understand and calculate theoretically what is the expectation value. And then once you have this implementation and you have also the QMod attached in the canvas, you need to code it in the Python. So the homework assignment will have to do the same thing to implement in Python, and then to do the post-processing using the Python SDK.